So in the previous videos, we looked at geometric descriptions of fluid flows. In particular, we looked at the concept of a streamline. In this section, we are going to look at Newton's second law along a streamline. That is, if we apply Newton's second law, the sum of the forces along is equal to the mass times the acceleration along a streamline, we're curious to see what this will give us. Now we're going to look at a specific class of fluids, which is called inviscid flow. Inviscid flow is an idealization where we assume that we have a frictionless fluid. So that means no viscosity. Certainly, this is never truly the case. However, this can often be a good approximation, particularly when other forces, such as pressure forces or gravity forces, are much more dominant than the frictional forces. Furthermore, in this section, we're only going to consider steady flows. That is, at a given point, the flow properties, such as velocity, pressure, temperature, remain unchanged with evolving time. So here I drew a streamline. So here's our streamline right here. And I've set up a coordinate system. So we're going to look at an SN coordinate system. This is a curvilinear coordinate system where S is in the streamwise coordinate. And here this N is the normal coordinate. Now yes, this might seem, we're going to go through a mathematical derivation, but I think it's so important because the results of this analysis here and this final equation that we come up with, Bernoulli's equation, it is very powerful, but it is, it's so important to know where it comes from so that you know where to apply it. Bernoulli's equation applied to a flow where its assumptions do not apply will yield to some very bad results. Okay. So we're going to be looking at Newton's second law. Sum of the forces is equal to the mass times the acceleration. So let's look at the acceleration of, a particle. The acceleration A, what is it going to be? It's the time rate of change of the velocity vector. And so here we have an SN coordinate system. So we can say that in the tangential direction, or in the streamwise direction, we have dv by dt. In the S direction, plus the centripetal acceleration, v squared over r, and that is in the n direction. So this is the streamwise or tangential acceleration. So let's call it streamwise here. And this is the normal acceleration or centripetal acceleration. The latter being due to a change in direction. Okay, we'll come back to the acceleration shortly. Okay. So what forces can act to accelerate a fluid particle? So in a typical fluid, we would consider pressure, gravity, and viscous forces, or shear forces. So if we were to look at a differential volume, okay, then our forces, dF, would be equal to our pressure forces on our volume plus the gravitational forces on our volume plus the viscous forces on our volume. So again, we are looking at inviscid flow, which is a frictionless flow. So there's no viscosity. So we're just left with these two terms. Okay, so Newton's second law applied to So let's write the Newton's second law applied to a small volume dV, we would have dF is equal to our mass times the acceleration. So we have rho dV, which is for our mass, multiplied by our acceleration dV by dt. Okay, so here we have the mass, and here we have the acceleration. So what we're going to do, we're going to look a bit more closely at this differential volume. So again, up here, we have our streamline, and we have a volume over here. So the fluid element has a volume given by ds, dB, dn, where ds is the length along in the streamwise direction, dB is into the page, and dn is normal to the streamwise direction. Okay, so let's apply Newton's second law along the streamline. So along the streamline, we have the sum of the forces in S. So now we're dealing with a scalar equation. Is equal to the differential pressure, and again in the S direction, plus the gravitational force in the S direction, and that will be equal to your mass times your acceleration. Now your acceleration, dV by dt, we're only interested in the acceleration in the S direction. So we are going to project it in the direction of the unit normal vector in the S direction. So again, here is your mass, and here is your acceleration in the S direction. And this dV over here is given by dV. So recall that we looked here on the left that the acceleration has two components, a streamwise and a normal component. So this dot product of dV by dt in the S direction is just the streamwise component, which is the change in speed. Change in speed. And this is the component that we looked at over here. All right, so let's look at a free body diagram over here of our differential volume. So our fluid element here, so again, we have a length ds along the streamline, and we're showing here the pressure on the faces that are normal to the streamline, or perpendicular to the streamline. And so we show the pressures, they're always compressive. And we have a pressure here at the center of the differential volume, P. So on the right face, it'll be P plus the change of pressure along the streamline multiplied by the distance that we have traveled, which would be ds over 2. On the left-hand side, we have the pressure at the center minus the change in pressure along the streamline multiplied by the distance ds by dt, ds divided by 2. We also have a component of the gravitational force that is acting along the streamline, and this is the gravitational force vector projected in the streamwise direction, so we're dotting it with S, and this will be equal to our mass, which is rho g dv, and then the component in the S direction, so we're going to multiply by the sine of theta. So Newton's second law for the fluid element along the streamline will be rho dv by dt multiplied by the volume. So this is your mass times acceleration term, is equal to P minus dP by ds, ds divided by 2, dB dN, then minus the pressure force on the right-hand side, so it's acting, so if this is positive in this direction, so it's acting in the negative direction, minus P plus dP by ds, ds over 2, multiplied by the area dB dN. And then we also have the gravitational term, so that's negative rho g sine of theta dV. So if we note, again, that dV is equal to ds dB dN, so we see that these terms appear everywhere, right? So these can cancel out. We can rearrange everything, which will give us rho dV by dt. We see that the pressure forces here, so P and P are going to cancel out. So we're left with the change in pressure along the streamline plus rho g sine of theta. And all of this multiplied by dN dB ds is equal to 0. Or we can just express this as rho dV by dt plus the change in pressure along the streamline plus rho g sine of theta is equal to 0. So what this equation tells us is that the particle will not change speed unless there is a pressure gradient, meaning that dP by ds along the streamline is not equal to 0, or theta is also not equal to 0, meaning that there is a change in elevation, which we'll look at a bit more closely later. So you might ask yourself right now, why are we even considering particle acceleration given that we limited ourselves to a steady flow at the onset of this section? So recall that a steady flow indicates that the field is unchanging with time. Okay? However, we're applying Newton's second law to a fluid particle that's moving through space along a streamline. So even though the velocity field is not changing in time, it is changing in space. Okay? So one would expect that a particle traveling through this space and it is experiencing a change in velocity, it would experience a change in acceleration as well. Or it will experience an acceleration due to experiencing a change in velocity. So even with this clarification and the reason for dV by dt appearing in a steady flow, let's get rid of the time variable. So we can write that dV by dt is equal to dV by ds multiplied by ds by dt. And this is just from our chain rule. So this is the change of the velocity along the streamline multiplied by the change in the streamwise direction displacement with respect to time. So this over here is just v. So we're left with v dv by ds. So substituting this back into our Newton's second law, we have rho v dv by ds plus the change in pressure rho g sine of theta. So hopefully you can see what we're working towards. So we are applying Newton's second law along a streamline. Okay. So what we'd like to do eventually is integrate this as the particle goes from one point on the streamline to another downstream. Okay. That is, we want to get rid of these differential terms dv by ds, dp by ds, etc. Before we integrate, we can do a few more simplifications. So first, we can write that v dv by ds can be expressed as 1/2 d by ds of v squared. Right, and you can check this for yourself. Right, the derivative with respect to s of v squared will be 2v multiplied by the derivative of v with respect to s, which will result in this left-hand side over here. Since the particle is following the streamline, we can set dn is equal to 0, so the total differential pressure, so the total change in pressure is equal to the change in the s direction multiplied by ds plus the change in the n direction multiplied by dn, and that is equal to. So let's see what this is equal to. So we are only considering the displacement along the s direction. Okay, so we can set dn is equal to 0. Okay, so what we recover is the change in pressure in the s direction ds. Okay, meaning that we can replace this partial derivative with just an ordinary derivative. So this momentum balance along a streamline results in 1/2 rho d by ds of v squared plus dp by ds plus rho g sine of theta is equal to 0. So we are very close to what we are trying to achieve here. Okay. So what we can do now, we can integrate along the streamline. Okay, so why don't we integrate this way and again this way. Okay, so we are integrating along ds along the streamline, and the right hand side will be 0 ds. So this simply reduces to 1/2 rho v squared plus p plus rho g s sine of theta is equal to a constant. Okay? And we see that this s sine of theta is just a change in elevation, right? So if we have a streamline here and we've gone along a certain distance s, and theta is something like this, and this is our s, then s sine theta is just this change in elevation, which we will call z. So this is change in elevation. So we have 1/2 rho v squared plus p plus rho g z is equal to a constant. And this result is what we call Bernoulli's equation. So Bernoulli's equation applied to a steady inviscid flow, Newton's second law applied to a steady inviscid flow results in this expression here, which is called Bernoulli's equation. Now, what does Bernoulli's equation tell us? So for these assumptions of steady, incompressible, and inviscid flow, this sum of 1/2 rho v squared plus p plus rho gz remains constant along a streamline. So if we have a streamline and we're going from point 1 to point 2, then there is a certain quantity defined by the summation of these three terms that will remain constant along this streamline. This is a very powerful result with a wide range of utility. However, application of this equation to the wrong problem can lead to very incorrect answers. And this is why we went through this derivation, to really drive home where this is coming from. So let's take a closer look at the individual terms in Bernoulli's equation. So first, from dimensional homogeneity, we can see that we have the summation of three terms, one of which is a pressure term. So this would suggest that all three terms have dimensions of pressure. So we have a certain quantity related to pressure that remains constant along a streamline. So this sum, some sort of pressure, is what we call the total pressure. So the leftmost term, I don't have it leftmost here, but let's rewrite this. We have P plus 1/2 rho v squared plus rho gz, each having dimensions of pressure, is equal to Pt, which we will call the total pressure. So this leftmost term here is called the static pressure. This is the pressure we're familiar with. Okay, this is the pressure that we've looked at before. It is the normal force on a fluid particle. This second term here has velocity associated with it, but if you work out the dimensions, it still has units of pressure, or dimensions of pressure. This is what we call dynamic pressure. And it's associated with the velocity of the fluid. And this final one should look familiar. This is the hydrostatic pressure. And is associated with elevation. So what Bernoulli's equation tells us is that the total pressure remains constant along a streamline of an incompressible inviscid flow. Okay, so the total pressure is constant along a streamline. And this powerful result allows us to further analyze fluid flow problems, and we will look at this in more detail in the next video. So what we have done here, we have considered Newton's second law applied along a streamline in an incompressible inviscid, and steady flow. We've applied Newton's second law to a differential volume. We've looked at the different pressure forces, the different forces that can act on this differential volume, which are pressure and gravity. We've integrated it along a streamline, and we recover what is called Bernoulli's equation, which states that there is a certain quantity called the total pressure that remains constant along a streamline. In the next video, we're going to look at application of Bernoulli's equation.